Okay, so now we're going to look at part 2 of matrices. And the first thing we'll talk about is matrix multiplication. Here I have two matrices, A and B, where the order of these matrices are RA by CA and RB by CB. And in order for these two matrices to multiply, the column of the first matrix must be equal to the row of the second matrix. When this happens, the result of multiplying A and B would give me a matrix that has an order RA by CB. Now, if the column of the first matrix is not equal to the row of the second matrix, then we say that this matrix cannot be multiplied, so it's non-conformable. Now, if you understand this, pause the video and see if you can figure out if these matrices are conformable or not. I hope you had answered all correctly. Now, let's look at matrix multiplication of conformable matrices. Remember, conformable matrices is when two matrices can be multiplied. So, if we have two matrices A and B, and we wish to multiply these two matrices, the column of the first matrix is equal to the row of the second matrix, and the result of multiplying these two matrices would be a 2 by 2 matrix. Now, there's a particular way to multiply these matrices. If we want to find the value of position row 1 column 1, to find this value we take row 1 of the first matrix and we multiply it by column 1 of the second matrix. And this is how we multiply it: 1 by 1 plus 2 by 3. Similarly, if we want to find the entry of row 1 column 2, we take the first row of the first matrix and then multiply it by the second column of the second matrix. So that's 1 by 2 plus 2 by 4. Again, if we want to find the entry of row 2 column 1, that will be multiplying row 2 of the first matrix multiplied by column 1 of the second matrix. So that will be 0 by 1 plus 8 times 3. And lastly, if we want to get row 2 column 2 entry, we take row 2 of the first matrix and we multiply it by column 2 of the second matrix. So we get 0 times 2 plus 8 times 4. And so we get 7, 10, 24, and 32 when we tally the entries. Now let's look at another example. B times A. Notice I switched the order. Now B times A is the same as the first step. To find row 1 column 1, we take the first row of the first matrix multiplied by the first column of the second matrix. To get row 1 column 2, we take the first row of the first matrix multiplied by the second column of the second matrix. To get row 2 column 1, we take row 2 of the first matrix and multiply it by column 1 of the second matrix. And then to get row 2 column 2, we take row 2 of the first matrix multiplied by column 2 of the second matrix. And then when we tally these entries, we get 1, 18, 3, and 38. Now if you realize A times B is not the same as B times A, so we say that this is not commutative. Okay, so matrix multiplication is not commutative. Now let's look at another example. I have a 2 by 3 matrix multiplying a 3 by 1 matrix. So then my result will be a 2 by 1 matrix. And to get row 1 column 1 entry, I take row 1 of the first matrix and I multiply it by column 1 of the second matrix. So I'll get 1 by 1 plus 3 by 2 plus 9 by 3. And then to get row 2 column 1 entry, I take row 2 of the first matrix and I multiply it by column 1 of the second matrix. So that's 5 by 1 plus 5 by 2 plus 7 by 3. And when we tally these entries, we get 34, 36. Now you can pause the video and try to solve the multiplication of these two matrices. And the answer to this problem is 824. Now we're going to look at the determinant of a 2 by 2 matrix. So we have matrix A, which is A, B, C, D. the determinant of A is just A times D minus B times C. And this can also be denoted as putting A between two vertical lines. Alright, so for example, let's say A is 1, 4, 2, 3, then the determinant of A will be 1 times 3, that's AD, subtract 4 times 2, which is BC, and we'll get negative 5. Okay, so now let's look at a singular matrix. A singular matrix is just when the determinant of a matrix is 0. So for example, if we have this matrix A and we want to find the determinant of A and we get 0 as the answer, then this matrix A is a singular matrix. Now let's look at the adjoint of a 2 by 2 matrix. Again, if we have a matrix A, then the adjoint of A is denoted by just swapping A and D and then putting negative signs by B and C. So for example, if I have this matrix A, the adjoint of this matrix will be just swap 1 and 3 to get 3, 1, and then put negative signs by 4 and 2. So this is the adjoint of A. Now to find the inverse of a non-singular matrix, that is a matrix that has a determinant that is not 0, this here is the formula. So again, if I have the matrix A, which is A, B, C, D, the formula for the inverse of A, which is denoted by A quote-unquote to the power minus 1, that's equal to 1 over the determinant of A times the adjoint of A. So if we look at an example, if we have A as 1, 2, 4, 3, from before we had found out that the determinant was negative 5, and we also found the adjoint of A, which was 3 minus 4 minus 2 and 1. So then the inverse of A will be 1 over negative 5 times the adjoint of A. When we solve for this, we multiply negative 1/5 by each entry in the matrix, and so we get negative 3/5, 4/5, 2/5, and negative 1/5. So this matrix is the inverse of A. So now we will look at the multiplicative inverse of a 2 by 2 matrix. And one of the properties is that A times the inverse of the matrix is equal to I, and also the inverse of the matrix A times itself is equal to I, the identity matrix. So for example, before we had looked at the matrix A and we found its inverse, so then if we multiply A times the inverse, you can try it for yourself, you'd see that you'd get the identity matrix. And also if you swap it, if you say A inverse times A and you multiply these matrices, you'll also see that you get the identity matrix.